It's extremely hot in here. Okay. Um, so we are recording. Let me share the screen. Okay, so we are now recording. So let's start here. Neural input optimization. I put together a repo that you can use for reference. I'm still updating this repo, but it's in good shape now. So there is this README that we're going to go through today. Additionally, I've put together a few folders. I got some data sets here, chocolate data set, materials engineering data set, portfolio, vet data set. These are synthetic data sets that I've been putting together that would relate to neural input optimization. You can look at these as reference just to get an idea, but you should really use real data. Okay. So this Chat GPT, I generated some data. It's basically, um, you know, but yeah. So I have some information there. If time permits, we will go over the passwords NIO approach. Maybe towards later in the semester. I will post the paper and the code if you guys want to review that. And then the focus of today will be more of the classical example of NIO, which is an industrial application, industrial settings, material science, right? So you want to generate, as I said, a material with a certain properties, right, through the production process. So what are the inputs in the production process that will result in that material for, from your plant or company? So that'll be the example. But today I'll start the first half. I'm going to start with just a more, what the description of it, a more formal description of it. I do have, as usual, like a toy example of the technique just to give you the overall simplest, clearest picture of it. We can run that in on Colab easily. And I think you should get the gist of it. And then we'll start working through a more realistic problem that's a little bit harder maybe. All right, so let's get into it. What is neural input optimization? So neural input optimization, NIO, is a technique that uses a differentiable surrogate model to reverse engineer optimal input values given desired outputs and constraints. Okay, so that's the key idea. Rather than relying on a black box search or trial and error methods, NIO trains a forward model, typically a neural network, to learn the mapping from input variables to output variables. Once trained, this model is used in reverse. It enables gradient-based optimization of inputs by minimizing a constraint-aware loss function, effectively inverting the system to find suitable inputs that yield specified outputs. So another way of thinking about this is, we're trying to figure out the inputs, right, that meet a certain level of constraints. So when we build a model, we give it inputs, it produces outputs. Well, an inverse of that would be that we train another model where the outputs are now inputs, the inputs are outputs. So that model given a vector, let's say I have a vector of 7 that produces a vector of 4. Well, the inverse of that is a model that receives a vector of 4 and produces a vector of 7. Do you guys see that? So those are inverse models. There's quite a bit going on there. Things like like theoretical, very elegant things like, is this model invertible? Can we even do that theoretically? So there's a lot going on there. And it's very interesting. And these have been around for, hundreds of years, probably, or 100 years in the optimization field. So as you probably know, the optimization field has been around for a long time. It was called operations research and all this, right? So that's not a mystery. What NIO gives you is a little bit different. So in neural input optimization, as the problem describes here, you're not doing trial and error and doing searches. NIO, essentially, you train a forward model. So the forward, vectors of 7 given vectors of 4, which is a neural net, to learn a mapping from inputs to outputs. Once trained, this model is used in reverse. It enables we enable gradient-based optimization of inputs by minimizing a constraint-aware loss function, inverting the process. Okay, and this loss function is now like the challenge, whereas before, or in normal machine learning, it's either MSE or cross entropy. Quite simple. Here, it's a little bit different because it's depends on your problem, right? So what I like about this methodology is it's going to give you a little bit more insight as and you can contrast with the normal approaches, right? So we're not training the model. That's not the objective. The objective is to actually figure out the input. NIO has broad applicability across domains such as engineering, finance, healthcare, material science, where stakeholders often know what they want as outputs, e.g. performance goals, target prices, biological responses, but must determine feasible inputs under real-world constraints. This is actually like every problem at every company. Okay, that's what's, that's why I think it's such an important technique, because a lot of people and companies will be like, oh, this is great. I give it an image and it tells me it's a cat or a dog, right? Or widget or something like that, right? And that's great. And I'm not, it's awesome, right? And GPTs speak, reason, all these things. But really, when you get to any company, it's like, man, I wish I could what is the problem? Minimize, the ultimate goal is to maximize shareholder wealth, right? So profits go up, expenses need to go down. It's this game, right? So I want to achieve these targets. Every company has that same problem. So what are the things you need to do? Increase marketing, buy technology, use ChatGPT, use AI. You know what I mean? Like, so what are the inputs to get you the output? Every company has this problem. And so now what you're thinking about is what is the specific thing in that company that you must address, right? And so that's what we're exploring here. Now, I've said that every company has this. Now, as far as research using techniques like this, it's mostly been in like material science, physics, chemistry. That's where this has happened, because you're usually trying to obtain a material or something with certain properties, and you have to have to find an optimization of inputs, et cetera, that achieve that goal, right? And this is data driven, by the way. So it's a data-driven approach where we collect real data, or it could be simulated data. Actually, as it turns out, the data that I'm using that is kind of proprietary was generated via simulation. But it's very, it's something called computational fluid dynamics, which is a thing that's like every industry does this. Every industry that has operations, like when they design the wing of an airplane, they have to run fluids over that wing, the air. That's computational fluid dynamics. Making that airplane is very expensive, right? So there's a whole field that creates these simulations of industrial processes, but and it's very expensive and it takes a long time to run these simulations. But once you do this, you can collect the data and then take a data-driven approach with machine learning to train some models. So that's kind of what we're doing here. So here, you capture some of the physics of some process, chemical process, something like that. All right, so so as I was saying, NIO has broad applicability across domains such as engineering, finance, healthcare, material science, where stakeholders often know what they want as outputs, performance goals, et cetera, but must determine feasible inputs under real-world constraints. For example, and here's a case of a veterinary use case. So a veterinary use case might involve identifying safe and effective dosage combinations of antibiotics based on desired recovery outcomes and species-specific tolerances. So you can see, right? So there's variation here. If you've collected all that data as you're, conducting your operations for 10 years, then you have that data set. Now you can build a model of inputs to outputs and now use NIO to figure out optimal inputs. Make sense? So this is the idea. So today, as I said, I'm providing I have those data sets. We'll discuss them in a little bit. I created them only to give like illustrations of what you can do. In this way, NIO acts as a decision support layer that enables fast control experimentation across complex multivariable systems. Unlike a simulation, yes. Yeah, please. Yeah, that's a good idea. Like a generative image model. Oh, I see what you're saying. So I give an image of a cat and a dog. It says cat and dog. So now you're saying reverse it. It's cat and it produces a cat. The only issue I may see with that is that just those two variables as information may be limited. Do you see what I'm saying? But it's something interesting to explore. Yeah. So yeah, you're generating the input image, but see, it's always cat or dog, right? So I think that's a weak point. But it's explore that further. I would recommend. Okay. Yeah. So yeah, in this way, NIO acts as a decision support layer that enables fast control experimentation across complex multivariable systems. Okay, we got a paper coming up. As I said, it just hasn't been published yet. Once it's published, I will paste it here. And this is the example of the password generation, which actually, that's another thing. So the password generation one, although you're trying to optimize for the inputs, it was really the thing that was being generated was still in the output. Do you see that? So in your example, this generative approach could still be here in the output layer. It could generate images and you're optimizing something over here because you also have constraints, right? So that you like a loss function that you have to create. So just think about it a little bit further, but yeah. All right, so NIO applications. So there's this one in cybersecurity where I provided some code. So for those of you that might be interested in something related to language, like this one, which was related to passwords, you can click on this one. And although the paper is not there yet, you can take a look at this, passwords and constraints. And, go to the latest run. Like this one. And this is an application of NIO to generate passwords. So this produces, you can see, let's imagine that the constraints are for the pass. Well, first of all, it has to be secure, which it is. But the constraints are that it needs to generate passwords with characters, lowercase, uppercase letters, numbers, which are digits, and special characters, right? So you can constrain it to produce that, which is this. You can see these passwords have everything. Or in its generative, I can generate as many as I want of these tokens. Or no special characters. If you notice carefully, there's no special characters. These were generated. No special characters whatsoever. No digits. If you look carefully, there's no numbers in here. This is not a 1. This is an L, for instance. So no numbers. No lowercase letters. You can see all uppercase. No uppercase letters. No special characters, no digits. No special characters, no digits, and no lowercase letters. You can see it's mostly uppercase letters. So they're generative in this sense. NIO can help you. I think you're all also thinking about this the same way. But yeah, this is for something related to strings. So it doesn't just generate numbers, it can also generate letters. How does it do it? Pretty much how we did it with the LLM. Instead of having that vector of 50,000, we just have a vector of 70 of the characters that we want. And eventually for every letter in the sequence is finding a probability of which character it should select, which one has the highest. And you can use NIO for this. Yeah, go ahead.
Why? Do you have to model
There was no thing to train here. That's the other thing I should say. So this is an example where that technique is used, but there was no model that needed to be trained. So there was no step one, like we will do today, where we train a model, and then this just had a simple softmax and a ReLU, and that's it. And so, but the input is still the thing that is being optimized. It's just it's a vector that's like something, an embedding, essentially, if you want to call it that. So you're just giving it an input. You're optimizing, imagine you start with the input as random, and over the training, that becomes something meaningful that when it goes into the pipeline, it'll produce the passwords as you want it. So it's still optimizing the input to produce the outputs. It's not optimizing the outputs, essentially. Yeah, go ahead.
the input is not the password?
No, it's not the password. And this might confuse you, but actually, when we look at GANs, generative adversarial networks, you will see that that's the same idea. So GANs are image generation. So when we cover CNN and stable diffusion, in there I'll squeeze in GANs. GANs generate an image as an output. What do they use as input? Some random vector goes in there. Do you see that? So that you will see that later. There's no input. Essentially, something goes in, vector of 100, why not? And it produces an image. And then the way that it works is there's actually two models. Then there's a classifier that looks at that image and it says, oh, that's not a cat, or that's a fake image or whatever. That feedback is used back to optimize, and so, but the model is optimized, not the input. Do you see that? Here, similar idea, but we optimize the input, not the model. Okay? So try to understand this one, because I'm jumping the gun here by talking about GANs, but GANs, just be aware, they kind of work like that. A lot in a vector, something has to go in. That's the thing. Neural networks need something to go in, right? And it can be a random vector that produces something, and then something else provides the feedback, like a neural net, but you're updating the weights of the model, or like in NIO, something goes in that you're optimizing, so that it becomes a nice input given what you're using here, model or not, to produce something. And you can use either the output here or this input here. So there's flexibility. Any other questions? So anyway, so those are different ideas. Don't confuse GANs and this, although there are similarities, okay? But the key thing with this one, neural input optimization. So the goal is to optimize only the input itself. Okay.
In specific case?
Which case? Okay.
Once you have optimized the input, you have to certain number of nodes that we use natural password.
Sure, that's true.
If you want
a batch. Yeah, that's actually how we did it. So we had 2048 by, I forget what the input size was, but 2048 was the batch. So that's 2048 passwords all at once. Yes, exactly right. Exactly right. Because it's like input goes in, output comes out, feedback, and you keep doing that in a loop to improve this input until after 20,000 iterations, this is good. Now it goes in and you get the final set because this is good to produce this. See, you're training this to be good so that it outputs the thing that you want.
So you have never done.
You've never done training. Yeah, it's an art, not a science. You know what I mean? Like you don't quite know when you have to. That's why when you guys do your project, you'll have to look at your results because also it may just learn really quickly. Like it starts producing sort of what you want fairly quickly, and so it shouldn't take forever. Yeah. Uh-huh.
Something.
That's right. It's fast.
Yeah.
That's right. This one cannot be deployed with Onyx. Yeah. It's a good observation, right? So this has to be deployed more as a service, which is what I was saying, like fast API. So it needs to run and then you make the call to it because, yeah, that might be, you might consider that a downside or a problem or whatever, but hey, if I get an extra $1 million for optimizing an input, I'm gonna do it, right? So it just depends. It's here the goal is the input, but you need stochastic gradient descent to happen and differentiation, and that happens with the torch framework, the derivatives part. All right, good. So anyway, so as I was saying, this is an example. We just wanted to show you. I know I'm kind of glossing over this code because it's my second example, if at all, right? But I wanted to show you that it is possible to generate text. Someone is thinking of images already, and that makes sense. The example I'll give you today is more regression. Input regression, output regression values. It's more intuitive case that we have. But here's an example, and you'd be surprised how many of the ideas from here are related to the LLM, right? So it's going to be like masks and predicting a probability distribution and things like that. All right, so we can go back where we were. Yeah, so the first half of today is just really like to give you ideas for the project, okay? All right, so we've done this description. Another application is industrial blast furnace applications. This is actually the one I'll discuss today during the second half. It's an intuitive case that I've been using a lot. Reasoning is another example. There's a nice paper here, very impressive actually. If you guys want to take a look at it, reasoning through optimization, embedding a learnable calculus engine in large language models. So you guys know everything about LLMs now, right? And you understand the architecture, the blocks and everything, and the attention mechanism, and it's all matrix multiplications. And we know that LLMs are very smart and they seem to reason. Somehow that's been infused in their neural networks, may not be perfect. And also humans, reason, like we reason. But do we reason like stochastic gradient descent? That would be a very interesting question to answer, right? My feeling is that we don't, right? I don't think we do that. What do I mean by that? I mean that in my brain, I would have to, have this representation of a function, and for all the variables, at some point in time, I take a derivative of it, and I would know then if I'm going to update something positively or negatively, right? And I have to do that. That's essentially using stochastic. That's how we train models with stochastic gradient descent. But that happens in PyTorch as we're training the model. That's what opt does when we take that step, and the update, right? But in this idea, it's basically about introducing NIO into the LLM architecture. But everything is possible. Like you could have a few blocks where there's some kind of recursive thing, a random input goes in, that's doable, goes through that network, totally doable. It produces an output, right? that output gets compared to something, but then, okay, let's say we accomplish all of those things. How do you differentiate inside the LLM? You can't do that. Why? Go ahead.
I might completely.
Yeah.
But like when we're optimizing the input, it's similar to like what a image generator that takes your very simple input that you put. If you go to Gemini image creator, right? And you say, give me a cat.
So the text that you put in to generate, yeah,
Wizard. But then when you actually look into the LLM, it's like this whole paragraph that it actually created and submitted to its image.
so it took your input and it added more to it,
Yeah.
more context, etc.
Yeah.
To produce a better image. Yeah,
Or that, you think that's just going through the language model just to
yeah,
make it bigger and then.
there's different approaches. At the end of the day, I will say is vectors going in and vectors coming out, right? And they're being processed through the model. The difference here, the only difference, everything else is the same, is what we're optimizing, right? So when those models are trained, like that model that generates image, the model itself, the weights of the model are being optimized. Here in this approach, only the input.
Well, that's what I was wondering.
Yeah.
Is that what this is doing?
Well, actually, it's
user give.
So
What kind of crap?
give me a second to talk about these two ideas here, which are actually about LLMs. So that might give you a little bit of insight because it's research that's being done already. Okay, but yeah, so and then I'll take your question again. How about that? All right. So yeah, great questions. So yeah, so I was doing the reasoning thing. So I wanted you guys to understand, when we deploy an LLM, even ChatGPT is deployed in inference mode. So that means that when you're talking to it and whatever, it's not training then. It's only running, okay? They may be saving the data that you're entering to use later to train it again, but it's not being trained. There's a difference between train mode and inference mode, right? In train mode, you're running the model in a PyTorch environment, for instance, and you have AutoGrad. AutoGrad is the thing in PyTorch that does the differentiation. And then when the model is trained, you deploy it, as you guys have learned with Onyx, and you're going to put it on a website. That's not being trained anymore. It's an eval mode. It's an inference mode. What this is saying is, if you wanted to have NIO in the LLM that's in inference mode, right, you would have to put it in as an architecture. All of that is doable, but how do you add AutoGrad in there? That's not possible currently. The only thing I could say is, humans do learn how to do calculus, right? So essentially what you could potentially think about, which is what this paper thinks about, is that they essentially try to create neural networks that can do calculus. So that once those neural networks are trained to do calculus, they could also be in the LLM. And so when they have to do the differentiation inside the neural network, it wouldn't be AutoGrad from PyTorch, but instead the neural network that would do that differentiation so that now you have then how to update the weights. Do you guys understand? Because the key thing here is that you have to do the differentiation in the process. Any questions about that? Yeah, so this is what I'm trying to get you guys to understand is, when we train a model in PyTorch, right? We're using PyTorch, we do that optim, step, etc. So there's something called AutoGrad that's optimizing. We talked about this briefly last week about cross entropy. Remember, we update the weights of the model, right? And to do that, we take the derivative of all the partial derivative of the function at that point in time with that given weight. And that gives us, a positive or a negative. So if we have a weight, now we know plus or minus the learning rate so that we can do the update. That information is the key to all of this, right? That's how we optimize models with that technique. And with NIO, we also optimize the input via the back propagation. But that's not something that's something that only lives in PyTorch, okay? During training. It doesn't live in, is not available during inference mode, unless we somehow put it inside the neural network itself. Got it? Got it now? All right, so that's just another idea. You can explore that if you'd like. Here's a nice paper. This paper is just talking about how to train neural networks that can do calculus. Essentially make neural autograd. You can see it's even written here. A neural autograd. But so far, this does not exist. All right, I talked about AI auditing or token generation. So we went to the script for that. So I can skip that. We'll come back to this code today. This is the baby NIO, if you want to see it that way. It's the simplest implementation that we can do. And then we will move on to the other implementation that's a little bit more complete. Yeah, I've talked about this. Now I'm going to go to your question, right? So about large language models. So here are two examples where this type of technique has been used in large language models. So one is triggering target output text in LLMs. Okay, so we have a large language model and we want it to generate toxic language, bad language, right? So what is the input? And I'm not talking about through ChatGPT because ChatGPT has a lot of constraints. We're talking about, you downloaded Llama 3.2, just the model itself, maybe with Ollama. You give it text, it produces text, and that's it, right? So how do we trigger target output text in LLMs? Well, you could just type things and see what you get, right? That's kind of the approach, and then try to figure it out. Or wouldn't it be nice if I want you to generate this type of text here? What's the input that needs to go in to produce that output? Do you guys see that? And so this is another approach. So you can use NIO to discover inputs, e.g. embeddings or prompts. Notice that prompt would be maybe the text. Embedding is when that text has been converted into the numbers, essentially, right? So use NIO to discover inputs, e.g. embeddings or prompts that make a frozen LLM. Remember that because you're trying to optimize the input, you will freeze the neural network, in this case, the whole LLM, so it's not updated. That make a frozen LLM produce specific output completions, such as toxic language, jailbreak instructions, or sensitive policy violation. This is a form of automated red teaming where the optimized input is crafted not by manual prompting, but by gradient descent. And again, this is what I'm trying to stress with you guys, right? So I'm a human, let's say I consider myself the smartest, best prompt engineer in the world, and I go in, I don't know how I'm doing it, right? And I'm not guaranteed to be the best. What's the best? The thing that optimizes. So whoever is using gradient descent to obtain the input, that's who should win, right? Because gradient descent is an optimization technique. Do you see that? So basically, another way of saying is, whereas you get to 60% accuracy, stochastic gradient descent will get to 80% accuracy. It'll find that extra because it'll just push things just a little bit further so that it optimizes correctly. So this allows auditors to systematically search for edge case completions that may not be covered in traditional evaluations. So for this one, let's switch over to the whiteboard just so that we can understand one simple basic idea. And then Mike, is it Mike? Matt, sorry, Matt. And then we'll go to your, you can ask your question again. See if okay, so in normal NIO, right, we're going to have an input, let's say a vector of 7. We have our model, and we have our output of 4. Do you guys see that? This 4 comes out. You compare it to some constraint via the loss, and you optimize, right? So you're optimizing this one here. These input values get optimized via backpropagation. What's important to understand is, for the simplest example, these are just regression values. Do you guys agree? Just, they're just numbers. 25, 27, 30, whatever. Should be scaled probably. Scaling is always helpful with neural networks, right? Okay, with a large language model, and we freeze the model. We've established that. With a large language model, what do we know? We provide text, right? We got some Huckleberry Finn, something like that. And then the output is also Huckleberry Finn. Do you guys agree? Yeah. But we know that this gets converted into numbers, right? You guys already know this. You know that the input and output is actually pretty straightforward in large language models. It is a tensor of batch size, comma, sequence, right? Comma, the embedding size, right? 256 or something. That vector 256, so if I grab that vector here, a dense vector of size 256 is made up of numbers. Guess what? That looks exactly like this one, right? So that's exactly the same. Just more, right? Because now there's going to be batches, sequences, embeddings, but essentially one embedding of 256 you could think as equivalent as a vector of 7 here. And the backpropagation to 7, 256, or n by sequence by 256 is totally doable. That's not a challenge. It's just coding, right? But you guys, that's supported. Does this make sense here? And so now this tensor, what do we know about it? Let me change. Gonna continue. Yeah, continue. Red. And then here, this tensor then goes into the LLM, which is just a model, and you freeze it, right? It's totally frozen. Or you could freeze some layers and not freeze other layers, or remove some layers and keep some layers. It's entirely up to you. But in this case, we do a complete one, and this produces another tensor of the same wave, which will become text. But at this level, if we kind of look at one of these, batch by sequence position by embedding, we bring out a vector of 256, right? Or something like that at some level. And then guess what? If I use green again, that's exactly like the output. So essentially now what you can do is, or you could use the text, it could be at the text level, and it's, however you want to do it, but you could somehow then, this is going to produce a tensor that when converted is going to be toxic. So you then just need to optimize this tensor here to produce those desired outputs. Do you see that? So this is a technique that has been attempted to not generate what are the inputs in text that would generate toxic, but what are the inputs at the embedding level that would generate the desired toxic output or whatever it is. Got it? Yeah. All right, so that's one example. The other example is even more interesting, but someone has already attempted this as well, and that is I'll describe it in a second in the text, but if we think this is the LLM, and actually I'm going to draw the LLM like this. if this is the LLM and it's got, as you guys know, blocks, you want to know, this was text that came in that became the tensor that goes into the large language model like that. So another approach has been for privacy and data leakage. People have tried to figure out, well, I grabbed this embedding here. What is the possible text that created that? So another way of saying it is, this knowledge, where did it come from? Right? And so they have tried to do this, and it's better articulated in the paragraph that I'll read to you. But yeah, that's the idea. You grab like an embedding and you kind of try to figure out where did it come from. And let's say that you discover, well, this produces text that if we look at it, it looks a lot like the Wall Street Journal. So this came from the Wall Street Journal. Or guess what? We look at this and this came from proprietary documents from, I don't know. Yeah, well, hopefully, probably not that, but yeah, it came from the Federal Reserve, right? So some secret that were supposed to be protected from the Federal Reserve. So one example I've given to students in the past is, well, think about how we do division, right? So we divide things. Let's say I'm going to divide. I learned how to do it this way, right? You put a number here like 40, and then 40, and then you put a 2 or something, and that's how I learned. But there are other ways of doing this. Like I think there's one like this or something. And that's another approach. Which one is more efficient? Who knows? But my point is, I learned this approach. And so this approach could be what's in this embedding. Do you see that? And so somehow then you could figure out that the input that generated this knowledge was, well, it keeps generating this symbol. So you know then where it came from. Or when you reverse engineer this from the embeddings to this, it does the other symbol. So then you know, okay, it came from books with that approach. This is a very simplified way, but just to give you something that's binary like that. Do you guys see what I'm saying? So let me just summarize that, then we'll go back to your question, because I do have this. So these are just a couple of papers that I found that I wanted to tie to both LLMs and this technique. So this is called, I guess, representation leakage auditing. This is actually a really important problem. I don't know if you guys heard, Anthropic settled with one company, like the Wall Street Journal, let's say, I don't know, for a lot of money, right? Because they had trained their models with their data, and now I think they have some scheme where new data they have to pay or something like that. So it's really big business. This was in the news, and it went to court and everything. So it's an important problem for sure, worth a lot of money. So representation leakage auditing. Use NIO to recover or approximate the original input that produced a known internal embedding or hidden state. This method tests how much information about the input is retained and potentially leaked through the model's representations. So you guys might, everyone initially thought, well, it's a neural network, it's all numbers. Who cares if we train with, someone's data? They'll never figure it out. Well, as it turns out now, they're trying to do this so that they can figure out where it came from. This method tests how much information about the input is retained and potentially leaked through the model's representations. It's useful for auditing risks related to memorization, privacy violations, or information leakage in embedding APIs and transformer models. Yeah. These use cases reframe input optimization as a structure, constraint-aware audit tool rather than adversarial attack, opening up new applications in AI governance, safety, and risk assessment. So, type of auditing. Yeah, good.
But with this technique, we can
Yeah, like the average. We can get the average of it, possibly.
not the data.
Well, the training data goes in as input. So you'd be trying, I mean, you'd be trying from that embedding to like we did a batch. So maybe from that embedding, produce batches of the input. And then taking those numbers back to text to see what they look like. And to us, they may look like nothing, like gibberish. But if there is a distribution there of something, that you may be able to tie it. So for instance, it's all English. And from all English, it's all newspapery text, or it came from Stack Overflow or something like that. So it's like, it has that structure of code. So you're not specifically getting one thing, I would say, but like a distribution of it.
It's actually finding the one you're thinking.
Yeah, exactly. You're not gonna get like article from Monday, necessarily, but you might get statistics of what that input data look like because all that input data going in produced that embedding. Do you see what I'm saying? So it learned from if you started giving it all that data, it would start updating. Here you're trying to do it in reverse and obtain not the exact articles, but just like an overall average of it, like a distribution of it. So for instance, like I said, you might be able to tell if it's in English or another language, if it's like newspaper speak or is Stack Overflow, 4chan, something like that, which would be very toxic if you're trying to find, what the toxic tech. Yeah, you know what I mean. 4chan has been studied a lot. You'd be surprised. So, does this make sense, guys? Now, Matt, what was your question? Mhm.
Seems like more creative. Kind of like great.
Mhm.
We created as opposed to
Sure. Yeah, that's
as opposed to
the idea, right? So the inputs would be for generative purposes for like, as you said, testing new things or looking at a distribution. That's why they say it's like an audit tool. You think it's good? Okay. Any other questions, guys? So we've talked about how we can use it for passwords, give a couple of examples of LLMs, right? Someone's thinking about images, and I don't have an example for that, but I think that's a nice, interesting idea that's possible somehow. And then obviously we're gonna start with the more classic example of just regression inputs, regression outputs, and go back to this industrial setting. Okay. So this finishes this README. As I said, I did provide here this data, which, like I said, it's something I generated the other day as I was preparing for this, and it's just synthetic data, but it's meant to be kind of like for this type of problem. So a chocolate data set, I think it's like, you put in so much sugar, milk, temperature, maximize this, and then you obtain like sweetness, smoothness at a production cost per batch. Do you guys understand? And they're separated by input and output. So the I indicates input, the O indicates output. So you train the model for this, and then essentially, given these conditions, I get this type of chocolate. Now I want this chocolate. How do I backpropagate? What are the steps in the process to get the bittersweet chocolate or the very sweet chocolate or, something. Okay. All right. So another example, synthetic materials engineering data set, same idea. So I've got iron, carbon, chromium, the temperature in Celsius, a cool rate, pressure, some additive that gets added, and what are the outputs given that? Tensile strength, corrosion resistance, brittleness. I've been mentioning this a bit. So what do? This data set probably has 5,000 samples. And so you train the model, given inputs to predict outputs. Then your question is, well, I want a material with a tensile strength over 300 and a corrosion rate of between 0.12 and 0.18 for whatever reason, and a brittleness of 4 or above. Do you see that? And given those constraints, the outputs, what is the input that I need? So it gives me this, but not specifically one of these, because neural networks can extrapolate, interpolate, right? So it could give me perhaps an input that was not even in the data set. And that might be the eureka moment that your company says, whoa, wait a minute. We've never tried that. And you're saying that this is better than what Bob and Mike know. You know what I mean? So you see what I'm saying, guys? So there's the knowledge that you have, and then what you actually extract from the data that might just be 5% more optimal, but you're the better product once you have that. Questions on this one? All right, let's look at third one. Portfolio, for those of you that like the stock market, Bitcoin, something like that. You want to predict when you should invest, right? So you have stock, bond, crypto, real estate, cash, your risk appetite, time horizon in years, and then your outputs are expected return, risk score, maximum drawdown, ESG score. I don't know what that is, but something. So you say these are the parameters that I want. First of all, you train, right? So step one, you train the model with this, the inputs to outputs. Then you say in step two, I want of these 4 outputs, this one in particular, what is the input that generates that? The optimal input. And that's the case. And then the last one, vet data set. So veterinary medicine, so animal type, and notice this can be also like cats and dogs, so label type things. Weight of the animal, age, previous antibiotic, symptom duration days, temperature, severity, and then it's going to be prescribed dosage or dose, treatment duration in days, expected recovery days. So if you wanted to have this and this, what are the inputs that would generate that? Got it? So that's it. So that's essentially, hopefully these are examples that help you to better understand the types of problems. You can pick anything that you want. So it's, easy or hard, it's up to you guys. Just, I want you to do the methodology. I do think this method has worked well in the past, so hopefully some of you will have good results. And here there's a further description of these data sets, and a few other ideas. So it's just for you to read. All right, guys, any questions about these? So I think that's enough for motivation and types of problems that you can address with this, right? And we should now be ready to start looking at the code and, trying to solve this problem. Okay? Any questions? All right, great. So that is the overall description. So let's go back to the top of the repo. All right, so here I have the first piece of code, okay, to introduce NIO. So what I'll do is I'm going to end this video as just like motivation, and I'll start a new one just to the code.